afternoon and welcome. Good afternoon and welcome to the Jones Seminar. Today we are fortunate to have Dr. Eric Fossum, who invented the CMOS active pixel image sensor, which is the basis of essentially all cell phone cameras. So it's kind of a big deal. He received his PhD from Yale University and was a faculty member at Columbia before joining the NASA JPL lab out in California. With colleagues from JPL, he founded Photobit Corporation and had several management roles there. After that, he served as CEO for Simpel Corporation, which developed and made MEMS-based autofocus actuators for cell phone cameras. He presently is a consultant for Samsung Electronics, and I believe he has a tractor somewhere in New Hampshire. During his years as a technical and entrepreneurial person, he maintained an adjunct position at the University of Southern California. So he continued to do research and publish papers working on his own research projects. He has over 120 U.S. patents and has published over 240 papers in research journals. He's received numerous awards for his work, including the NASA Exceptional Achievement Medal, the Royal Photographic Society Progress Medal, and the 2009 IEEE Andrew S. Grove Award. He's a fellow of the IEEE and was inducted into the NASA DoD Space Technology Hall of Fame. And today he's going to speak to us about image sensors for digital cameras, shedding light on how they work. Please welcome Dr. Fossum.
Well, it's a pleasure to be here, and thank you for coming. I live here in New Hampshire also, and I really love New Hampshire, so it's really especially a great thing to be able to come over to my state, somewhere else in my state, and give this talk. I understand that this seminar should be educational. I understand that most of you are not experts in my field. So I'm going to talk about a number of different things. I'll try to make it as much continuity as possible between these different things. I hope that you can all take away at least something you didn't know before when you leave. I'm not sure if it's practical in such a large group to ask questions along the way, but I'm always open to answering questions either during or after. And by the way, last week I had the swine flu or something, I don't know, some nasty bug. And so my voice may leave me about halfway through, so if you see me popping throat lozenges, that's what that's about. Okay, so I hope that you, is there a question already? No. I hope that you can take away one or more of these key points. One is the basic concept of an image sensor pixel and camera on a chip, and how we form a color image in a camera. Let's see, a more advanced section would be on noise. Noise is always a very important part of any engineering device, although it's not often taught in a university. Some of the driving forces, technology, and limitations for small pixel development. You probably all have some sense that there's more and more megapixels in each succeeding generation of camera, and somehow they're shrinking the number and size of pixels in each camera generation. And then last, but hardly least, is my own personal pet project for the future, which is something I call a jot sensor, and try to explain to you a little bit about what that's about. Yeah, so I live over on Lake Winnipesaukee, and this is a picture I took with my camera, which is what most people do with their cameras, is they take pictures, and so that they can show them to other people eventually. I call that the being there syndrome, where you try to transport yourself in time and space to some other place through the use of a digital picture. And so the point of our camera, digital camera, usually is to make that being there possible. So let's talk about the basic concept. Oops, let's put that down. Can you hear me okay with this mic? Okay. So there are many kinds of digital cameras. The picture I took of the lake was with this kind of camera, digital single lens reflex camera. They used to have film in them, and now they have digital sensors and digital electronics. There's the point and shoot kind of camera where you don't have to think too much, you just click the button and take the picture. By far the most number of cameras that are made today are the tiny cameras that are inside cell phones. There's probably about 1 billion camera phones that will be manufactured in 2010. 1 billion. That's a lot per day, going into landfill probably in a couple of years. Of course, there's camcorders and webcams and cameras in cars, and this is a camera that's inside a pill that you swallow and goes down through your intestines. We did the very first camera for that pill back a number of years ago. Wireless cameras, and these are, well, they're not really cameras, these are digital sensors for x-rays in the dentist office. You stick this actually inside your mouth, and the dentist shoots an x-ray and captures an image of your teeth that way instead of the normal film approach. We did the very first sensors for these types of devices. And then just to be current, here's another application of cameras is for motion capture and for gesture capture, so that you can take images of the person's face and their body and transform them into something for movies. Since my other home is in Pasadena, when we started Photobit in Pasadena, we decided that actually Los Angeles is the image capital of the world anyway, so it was quite appropriate. Most of what we're going to talk about pertains to all these kind of applications, except perhaps X-ray cameras. The other thing that's important in any engineering project, but particularly here, is the human factor. So you take a picture and you look at it later on the screen. You want the picture that you see on the screen to be the way you remembered it looked when you took the picture, or maybe even a little better if possible. And there's a lot of things that happen between the time you take the picture and the time you see it on the screen. It goes through the response of the silicon device, it goes through some processing inside the camera, additional processing in the computer, and then even just to get from the computer to the screen, the LCD display, which is probably the most common, has both a backlighting spectrum as well as a color filter array spectrum. And when you put all those spectral responses together, you kind of hope that everything comes out the way you remembered it. And it's actually a lot of work to make that happen. Also, the human eye is not, well, depends on your philosophical point of view, whether it's the perfect camera or has some imperfections. But the human eye is responsive really to, at least for the cones, to 3 primary wavelengths. We call the long or red, the medium, which is green, and the short, which is blue. And these are all normalized to 100%, but actually it's quite different in each color. And then there's the black and white rod response curve as well. So somehow we see this scene according to these filters, and then our brain does something magical, and then we have to kind of recreate that process going this way. So in an image capture system, we have a scene, we have some lens to form an image on the detector array, which is divided into lots of picture elements or pixels. And then each pixel is sensitive to a very small portion of the image. Then these individual detector or pixel elements have to be read out through some sort of analog signal processor, converted to a digital format, through an analog to digital converter, and then through some image signal processor or ISP. And this is all usually not only inside the camera, not only inside the camera electronics, but often integrated on a single chip these days. Okay, so how many of you are electrical engineers? All right. I won't be talking to you. So each one of these pixels, well, consists of a, usually almost always silicon. And silicon is a semiconductor material. The way that works for being responsive to light is that, as you know, silicon, or maybe you don't know, silicon, like carbon or diamond, is a covalently bonded material. Every electron is very tightly bound together in the lattice. There are no free electrons generally wandering around. And in order to free up an electron, we actually have to come in with photon energy. And that photon goes in and breaks one of those bonds, has enough energy to break a bond, and the electron becomes loose, and we can use that electron to carry a little electrical current and get some signal out. And obviously the number of electrons that are free at any time is kind of proportional to the intensity or flux of light photons coming in. Okay, so in a, and I'm sorry, there's electrons and there's holes, but we won't talk about the hole part, we just count electrons. From a circuit point of view, that piece of silicon is represented by a diode. There's also some capacitance. Now I'm talking to the electrical engineers, by the way. There's some capacitance associated with that. And the first thing we do in the pixel is we reset this capacitor to some initial voltage, and then we open the switch. And when light shines on the semiconductor, a little current flows through this diode, which discharges that capacitor, so the voltage starts up at V reset, and then over time the voltage drops down. And the rate of change of the voltage over time is just proportional to the flux. So we've basically gone from light to electrons, and electrons to voltage, and from that voltage we can kind of infer how much light was falling on the device. So all we need to do is just read out this voltage and go into an analog to digital converter, and we've got back kind of a map for each one of these pixels of what the light intensity was. So there are other types of image sensors in the past. The most notable one was the charge-coupled device that was invented around 1970. It actually, the inventors received the Nobel Prize just a few months ago for the invention of the CCD. Fortunately for me, that's not the technology that's normally used now in camera phones. It's the CMOS active pixel sensor, which is kind of a second generation solid state image sensor. And it consists of a lot of photodetectors that convert the photons to electrons, and an amplifier that converts the electrons to voltage, just kind of the way we talked about, maybe with a little extra boost in there. And then we have some way to select a whole row of these at once, close all these switches, and we read out the signal from each detector down into the analog signal processor. Each detector winds up with its own wire through those switches. And in the analog signal processor, we can continue to suppress noise and further amplify the signal. And then one at a time, we can pick off each of the signals on these wires and send them to an analog to digital converter for converting them to bits. And then there's also typically timing and control logic integrated on the CMOS chip, and that's kind of the orchestra director for everything that's going on this chip. Yeah, so that's one way, and it turns out that these days another slight variation on that architecture is we can actually, for every one of these wires that comes down from the pixels, and by the way, there's typically thousands of them these days, each wire might be connected to its own analog to digital converter. Well, that means that there may be thousands and thousands of analog to digital converters on a single image sensor chip, which becomes more amazing the more you know about chip design, that you can actually do this. And some of the very faster cameras that you can buy now, like there's a new Casio HS10, I think, that takes slow motion images, maybe 240 frames per second, and you can play it back in slow motion, uses this kind of architecture in order to get that speed. By using the parallelism that's inherent in this architecture, you can really boost the speed quite a bit. So here's a picture of a camera on a chip. So the camera on a chip contains an array of pixels. The pixels are too small to see individual pixels here, and in this one there's only 300,000 of them. That's just kind of conventional, or old conventional television resolution, VGA, 300,000 pixels. The analog signal processor doing correlated double sampling to reduce noise, analog to digital converter, and a few other elements, and a big digital block here of logic gates to do all the logic functions and processing that's required. Okay, that's what a camera on a chip looks like. In that digital processing block is a lot of image signal processing, which is really quite extensive these days. We're going to talk about the color interpolation and color correction soon, but there's some other remarkable functions on there. For example, if you use a very small lens on a fairly big sensor, the edges of the chip don't get as much light as the center of the chip, just from an optical effect. That's called lens shading. And these days people actually correct for that as part of the image process. They artificially brighten the corners of the image. All kinds of exposure control, flicker detection. Fluorescent lights tend to flicker. That's kind of bad if it gets caught in your picture. Autofocus support to actually drive an actuator to focus the image. These kind of things are usually in that initial image signal processing circuit. Okay, so that's the basic concept. Let's talk about how a color image is formed. So the light comes into the sensor. This is kind of a cross section. Light or photons come in. The first thing they go through is a microlens. Here's a SEM photograph of some really tiny microlenses on the chip. And the light comes in, it goes through a color filter array, so we can select the wavelength of light that we want, green for example, so only green light goes through. And the microlens refracts the light rays so that it goes into the active part of the photodetector, because we also have wiring and other things that are not sensitive to light inside the pixel, like that switch or the amplifier. And having light strike that part of the chip or that part of the pixel is kind of a waste of light. We want to get all the light to the photosensitive part. So that's really what the microlens does. It's kind of a funnel to funnel the photons to the active detector area. If you look at the chip from the top in detail, this is what the color filter array looks like. It's a repetitive pattern of green, red, blue, and green actually. So we have two greens, a red, and a blue. And that pattern was first proposed by Bryce Bayer at Kodak a long time ago. It's called the Bayer pattern, and it's used almost in every chip. Not necessarily because it's the very, very best penultimate or very best or penultimate pattern, but because it is the patent expired. So everybody uses it. The patents are a big issue in this business. So in this case, when we put the green, red, and blue filters over the top of silicon, if you take the silicon response into account and the filter response, you wind up with, like the blue pixel has this kind of response. This is response versus wavelength, going from 400 nanometers to 700 nanometers. And these are pretty much centered where the eye is responsive. Blue is about 450 nanometers, and green is about 550 nanometers, and red is about 650 nanometers. So we try to get response out of each of these pixels centered on those things. Now those shapes of those responses are not exactly the same as the human eye response, and that's an issue. because when you start changing the response of the red, the green, and the blue compared to the human eye, when you reconstruct that color, if you don't do anything, the hue of the image is going to be changed or shifted a little bit from what we like to see. So there's going to have to be some color correction step coming up to fix that up. Now mostly when you take red, green, and blue images, it kind of looks okay. But we're also very sensitive to certain variations in color. Can you think of any particular color that we'd be very sensitive to? Or
White.
Pardon?
White.
Well, white is one. Your eye, you can, which is a different kind of problem called white balance, but your eye, no matter almost what kind of lighting you have in a room, your eye adjusts so that white looks like white. And but when you get your picture back, I'm sure you're taking pictures outside versus indoors at night with incandescent lighting. It's like, wow, there's that orange glow coming from. So you have to do a white balance. What about another color you said? Yeah, red, skin tone, that's the really key one. That's what people really are sensitive to. It's like, wow, that person looks green, they're sick or something, or too blue. And not only that, the strange thing is that different cultures like a little different color. So it used to be true in the film days, like Fuji film actually used to be a little greenish tint compared to Kodak film. And the same thing on sensors. There's a preference as to how people like to see color portrayed. So we have to take that all into account. Okay, color interpolation, what we really want for each pixels, we want to know the red, the green, and the blue value at that pixel. But if each pixel is covered either by a red or a green or blue filter, but not all three at the same time, we have to somehow reconstruct red, green, and blue at each pixel. And the easiest way to think about that is just interpolation. So consider this pixel here is covered by a red filter, so we pretty much know what the color red is at that site. And just as you might imagine, okay, we don't know what green is, but our next best guess is we'll take the average of the 4 surrounding greens and pretend that that's our green color, and surrounding 4 blues, and that'll be the blue value for that pixel. Works great most of the time as long as the colors are not varying quickly across the pixel array. If you have a sharp edge or something, then you're going to have a problem, an aliasing problem, because you're doing relates to sampling theory in a lot of different fields. If you're sampling at too low a frequency, you're going to miss sharp edge transitions, and you're going to get some weird effects. So I wasn't sure if this was going to come out or not, but it looks okay. So here's a nice looking picture, but if you look at the detail, like right here, you'll see that, you can see this, right? It's like orange stripes and blue stripes. Kind of pops out of the image, kind of a moire pattern. Same thing over here by the fence. Get these weird colors. So in order to get rid of that, you have to employ some sort of, they call anti-aliasing optical low-pass filter, which basically is the same as saying we're not going to let you perfectly focus the image. We're going to let it stay a little bit blurred so that edges do vary slowly relative to the pixel scale. I mentioned color correction. So the basic way to do color correction says, okay, you measured red, green, and blue, but that's not really what I want to show up on my LCD display. I want a slightly different variation of red, green, and blue. So I'm going to use this matrix, correction matrix, which is just shorthand notation for the math that says the new red is equal to this coefficient times the existing red plus a little bit of green plus a little bit of blue, and that'll be my new red. Likewise, the new green is a little bit of the red, hopefully mostly the green I measured, and a little bit of blue, etc. So we wind up with basically 9 coefficients that we try to match. Well, the problem is that we have a lot of different colors that we need to match, and with nine things to tweak, you can't get a perfect match for every single thing. So a lot of different strategies people take for this. They say, okay, we want green, red, and blue to come out perfectly, and we want the flesh tone to come out perfectly, and maybe pick a few other colors that people seem to be sensitive to, make those perfect, and we'll punt on the rest. Or we calculate some color average and weight different colors more heavily than others and try to make that come out right. And it becomes a big optimization problem to try to figure out the best coefficients in the color correction matrix. We're going to come back to the color correction matrix in a little bit. But I thought I'd just take a little diversion, talk about noise. As I said, that noise is often something that's not talked about too much, even though you probably all recognize it when you see it. Again, I didn't know how this was going to come out, so I had to exaggerate a little bit. I guess it looks okay. So this looks good, low noise. This is what noise looks like in a photograph. You can see that this should be a nice solid blue, but it's not. It's got other weird colors in it, different intensities, and there's other stuff going on here, so too much noise. And the holy grail for everybody who makes image sensors is to have the lowest possible noise. So one of the noise sources is fundamental, and that's called photon shot noise. So photons come from some light source, a distant star or something, a light bulb, and if you sit there and just measure, if you could, quickly enough, measure the photons coming in, they don't come in at a nice, steady, constant rate. It's more like cars on the freeway. They're and at very irregular patterns. So if you make a measurement, let's say you wanted to know what the average rate of cars passing under a bridge was on the freeway, if you just time for a very short amount of time, you could get completely the wrong answer, right? Depends on whether there was like 5 cars at that moment going through or no cars. You really want to average over a longer period of time. And the longer the time that you average over, obviously the better measurement of the average you get. The same thing is true with photons when they come from a light source. If you want to know how many photons are coming in on average, which is sort of what we see with the eye, you'd like to average over a long period of time. When you average over a short period of time, or not too many photons, then you start seeing a big standard deviation in the number of photon arrivals. And that's called photon shot noise. And if you count n photons, or n cars, the standard deviation goes like the square root of that. So if n is 100, then the standard deviation is 10. And if n is 10,000, the standard deviation is 100. Well, actually, it sounds like the standard deviation for 10 or 100 is less than the standard deviation for 100,000 or 10,000. But what we really care about is signal-to-noise ratio. And so the ratio of 10 to 100 is worse. Oh, boy, I got mixed up here. The ratio of 100 to 10 is much worse than the ratio of 10,000 to 100. So basically, the signal-to-noise ratio goes as the square root of the number of things that we count. So we'd like to have as many photons hitting every pixel as we possibly can in order to reduce noise. If we don't do enough, we get this shot noise pattern, which if you blow up some section here, even though this scene was illuminated by a constant light, which should be a constant light source, when you actually do the measurement pixel by pixel, you see that there's a lot of variation from pixel to pixel. And hey, this is a great experiment. You can even measure whether or not the whole standard deviation works with photons. So, as far as I know right now, the only solution to improving shot noise is to collect more signal. I keep hoping someday we'll find a way to beat back shot noise, or at least make it seem like it's not so bad, but so far that hasn't happened. Here's another type of noise, which is another fundamental noise, but you find it in circuits, and it's called reset noise. And if you have a battery and a capacitor, and you connect the battery to the capacitor by closing this switch, you expect the capacitor voltage to be exactly equal to the VA. And when you open the switch, there's no place for those electrons to go, so you expect the voltage to still be exactly VA. Unfortunately, that's not true. And the reason is that when you close the switch, think of this as kind of a drawbridge connecting two crowds of people on both sides. You have electrons, or people, that are wandering back and forth all the time, kind of Brownian motion in the wire. And when you open the drawbridge or you open the switch, there's always a certain number of people that are trapped on one side versus the other side, which you can't exactly predict because of this constant motion back and forth up until the moment you open the switch. So because it's thermally activated, it's no surprise that the formula winds up with a KT inside, and voltage that is KT over C square root. You will find, this always amuses me, you'll find a lot of circuit guys that will go to great lengths to try to derive this from some frequency response of a noise response of a MOSFET transistor or something like that. And of course you better get the same answer when you do that. But the noise is actually very fundamental. Even a perfect switch, a perfect switch is still going to give you some KTC noise. So for an example, if you have a half a picofarad capacitance, that's going to give you an uncertainty of about 28 electrons RMS. Now for image sensors these days, we expect noise levels that is like 2, 3, 4, 5 electrons RMS. So when we reset the switch in that pixel that I showed you at the very beginning, we have to do something else in order to suppress the noise. And the easiest way to do that is to reset it, but then instead of assuming that the voltage is VA, actually just go in and measure the voltage VA, but then let that photocurrent flow like we did through the diode earlier, and then measure the voltage again. And so by measuring that signal twice, once before and once after, once after the switch is open but before any photo signal comes in, and then after the photo signal, those two measurements are correlated. It's called correlated double sampling, and we can suppress the noise that way. The third type of noise is what we call a fixed pattern noise. This comes from the circuits that are built into the chip. And this is something we can solve. It's not fundamental, but it's always there. It's kind of like Murphy noise. They don't teach Murphy noise too much in the classes, but it's always there in your circuits. That's a joke, by the way. So, but fixed pattern noise is just very subtle variations between elements in a circuit. That when you have a large number of rows and columns, if you have some sort of driver that's driving the row, and that driver for this row is a little different than the driver for that row, or the sense amp for this column is a little different than the sense amp for that column, there's just a very, very slight difference. But your eye, unfortunately, is a very good pattern recognizer. So even though the absolute value of the noise, the fixed pattern noise, is small, wow, you pick it up right away. You can all see all these, both horizontal stripes and vertical stripes. If you actually went and measured it, you find it's not very big, but unfortunately for us photophiles, I guess would be the right word, wow, it's a big problem. It's a big problem when you're making big circuits. Now the human eye is mostly sensitive to brightness and green. That's why we do the sampling twice in the green in the Bayer pattern. And it has only secondary sensitivity to color, red and blue. In fact, the old color TVs used to have very low resolution on your TV screen on the horizontal axis compared to the green or brightness signal. But you never see it because your eye is not sensitive to those frequency responses in red and blue. So the luminance, the brightness as seen by the human eye, is mostly in the green, And when you display a standard RGB signal on a CRT, which nobody uses anymore, those phosphors have different brightnesses, and the luminance seen by your eye is about 70% from the green signal, 21% from the red signal, and maybe only 7% from the blue signal. And the luminance signal-to-noise ratio depends then mostly on the green signal-to-noise ratio. And how do we boost signal-to-noise ratio? We need more photons. So we always like to have as many photons as possible in the green in order to improve the signal-to-noise ratio. I told you we were going to come back to the color correction matrix, and we are. The color correction matrix can degrade the signal-to-noise ratio. And maybe it surprises you that just doing some math in the chip can really mess up the signal-to-noise ratio, but it's easy to understand. If you subtract two large, noisy numbers, the resultant signal is going to be small. But unfortunately, the noise doesn't subtract out. The noise adds. So you wind up with low signal and high noise. So every time you do any mathematical operation on real signals, if there's any subtraction involved, you're in deep doo-doo from a signal-to-noise ratio point of view. So in the color correction matrix, we don't want any negative values, if possible. Yeah. Anyway, the bottom line for noise is that anyone can make a sensor that works well in bright light, but the real test is the low light performance, and usually that's pegged at about 10 lux. This room, by the way, is probably about lit at about 400 lux. An average bar is probably more like 10 lux, something like that.
What's a lux? Define a lux.
A lux, okay, a lux is a measure of brightness as seen by your eye. So how bright is it in this room? Well, it's however many lux I just told you. And 10 lux is a lot less brightness. Unfortunately, you know, it's one of those human factors. Okay, it's not brightness as you'd measure with some sort of instrument normally. It's not photons per square centimeter per second directly, because it depends upon what the spectral mix is of the light. So it's relative to what is the apparent brightness that you would see with your eye, and that's what lux measures. Okay, so what's the state of the art these days? Pixel counts for consumers are in the 8 to 12 megapixel range, going up, but not going up quite as fast as they used to. We'll come to that in a moment. Professional cameras might be 20 to 40 megapixels. Aerospace might be up to 100 megapixels now. And the pixel size, individual pixel, may be as small as 2.2 microns or even 1.4 microns for common consumer applications. So pretty tiny stuff. Probably this chip represents the state of the art as well as any. This is a next generation television system, possibly next generation television system, ultra definition or super high vision sensor. You know, we went from regular TV, which was VGA or 300,000 pixels, to HD TV, which is about 2 megapixels. That's about a factor of 6 or something increase in pixel count. The next generation is going to go from 2 megapixels probably to 33 megapixels, or about a factor of 16 increase. My guess is I'll never watch a UDTV program on cable TV in my lifetime. But some of you may see it. Hopefully we'll see it. But it's pegged at about 33 megapixels at about 60 frames per second, which is about 2 billion pixels per second data rate, which is a pretty spectacular sensor. So where are we going? What is the driving force here? Let's talk about that. Here's the market. This is always an important number. Here's the important number. $4.3 billion worth of image sensor chips sold in 2009, more or less. Biggest share of that is a company called Aptina, second is Sony, third is Samsung, fourth is OmniVision. Hey, these guys argue all the time about these numbers. But I show this chart because my company, Photobit, was bought by Micron, and then Micron spun off a few years later, Aptina. So I'm the grandpa of this company, so I'm very proud of that. Anyway, $4.3 billion, a lot of money at stake. So people are willing to invest in R&D. So there are kind of two aspects to small pixels. One is smaller pixels means more pixels. Well, smaller pixels and more pixels. So the first is smaller pixels allow smaller chips. So that reduces the chip cost to the camera module maker. Basically, the smaller the chip, the less it costs. This seems to be the rule of thumb. Also, the lens that's required for a chip of a certain diagonal, say, the bigger the diagonal, the bigger lens, and the bigger lens, the more expensive the lens is usually. So that reduces the optic size and cost. And if you can make the camera smaller, it can go more places, which is very important for consumer products. Probably the biggest development just in the last couple of years, which you probably hardly noticed, is that camera systems got small enough to embed in the very edge of your laptop or the edge of your display. Almost every laptop now has a little camera built into the screen edge. So that's because the cameras themselves have become not only small in width and height, but also in the Z dimension and thickness, so they can fit comfortably into the width of these things. And of course, the more places they can go and the more desirable they are, the more you can sell. That's more money. On the negative side, the non-recurring engineering costs for a chip, that's things like how many engineers does it take to design a chip? And what kind of new fabrication process do we need to make the dimensions smaller? And what do we have to buy for new equipment to make bigger wafers in the process? All those NRE costs are higher. And strangely enough, the performance of the pixel wants to get worse as it gets smaller. The quantum efficiency tends to get lower. The signal-to-noise ratio tends to get worse. There's more crosstalk. The green gets into the blue. The red gets into the green. You can mix up the colors. That gets worse. Another thing that happens with moving to advanced design rules in circuit land is that we usually try to keep the electric field the same in semiconductor devices, even as we make them smaller and smaller. But because the dimension is smaller, the voltages also drop. And anyone who does analog circuits knows that lower voltages make it much harder to build an analog circuit. So those are negative things. And as I started to say before, smaller pixels means more megapixels, which is good from the point of view that higher resolution images for the same optics, it's nice to see better, more sharper. Pixel count often sells more cameras and gadgets. I mean, there's two cameras on the shelf, and one's a 1 megapixel camera and the other is a 10 megapixel camera. Which one are you going to buy? Well, actually, if they were like 5 and 6, you can obviously go with the 6. And that's just kind of marketing mentality that's taught us all to do that. Marketing is a very strong force. Not always logical, but very strong. Now also more megapixels sells more cellular service traffic. Bigger computers, better software, more new software, I should say, not better software, mass storage. So it's desired from that point of view too. But it's not always a good idea. The negatives are that the entering visible light has a diffraction limit, is getting into the diffraction limit zone with state-of-the-art pixel pitch. So there's really less return on the resolution as we make the pixels smaller and smaller. There's more stringent requirements on the optical system quality. Getting those megapixels off the chip at the same frame rate gets more challenging. If you've got 1 megapixels 30 times a second versus 10 megapixels 30 times a second, that's 10 times harder to do. And usually increases the power requirements as well. Now, how do we reduce the pixel size? Well, the brute force way is just use smaller line widths and processes. And that's got a force all to itself. That's kind of the nice thing about CMOS image sensors, is that we get kind of a free ride on the whole same technology that drives microprocessors to go faster and memory chips to have higher density. We get to use the same processes to give us smaller line widths and processes. We could reduce the transistor, we could be clever. Basically reduce the transistor count in the pixel by sharing transistors. Unfortunately, that's kind of been done and taken, so probably not much room there. We can add extra optical layers like a light pipe to funnel light better to the sensitive portion of the pixel. And then something we'll also talk about in a moment is backside illumination to allow front fill factor design. So, you know, this is a fun time for engineers that do pixels, because there's a new challenge every year and a half or something to try to reduce the pixel size, and all kinds of places to be as clever as possible. It's all hard work though. So this is what something cross-section of a chip looks like these days for a 1.4 micron pixel. This is from Aptina, my grandchild company. There's a Microlenses on the top, color filter, right? This is an SEM photo, so that looks a little bit funky. But
Material for the microlenses.
usually some kind of like a polyamide type material, not glass. And actually, to make these microlenses, sometimes all they do is they just put on a polymer material, cut it into little squares, and then heat it up in the oven so it rounds out. You just got to make the initial dimension and the recipe exactly right so that your cookies come out exactly the right shape. The color filter array, and then here's the metallization that goes on top of the pixel, and the actual detector is down here in the silicon. And there's this light guide or light pipe that makes sure the light that comes through the microlens and the color filter array goes into this total internal reflection light guide. It's like a little mini fiber optic piece in a way to make sure the light gets down to the pixel and doesn't accidentally go over to the neighboring pixel. So otherwise you'd wind up with like green light getting into a red pixel, which would be bad. So this kind of prevents that.
And what's that material?
The light guide, I think it's probably some nitride and silicon combination. Even though they're my grandchild, they don't tell me everything that's going on in their life. So, another trick that we developed is what's called backside illumination, and I don't know, my kids really giggle a lot when they hear about backside illumination, but it's, for some reason that's a historical term. So here's the cross section we just kind of looked at with the color filter array. Here, a microlens and some wires, cross section of some wiring, and we're trying to get the light down to this photodiode, so it's got to go down a long way. But it also has some implications for the optics, the main lens, that the angle the light comes in can't be too steep or too oblique, I guess, and still manage to get down here. In a backside illumination process, we start with this kind of basic wafer. Here's the substrate of the silicon. The back of the wafer is normally way down at the floor. We grind that wafer away till it's quite thin, and now the light can come in from the backside and shine into the photodetector part, and we can put a microlens and color filter array on this side instead. And that way we don't have to worry about these wires blocking the light from getting into the photodiode. So it gives us more freedom on the wiring or circuits that go up here if we have the light come in from the backside. But this is an extra processing step, so it costs more. Still, that seems to be the trend. Here's a cross-section SEM photo from Sony, which shows the microlenses on the back, the filters, still some metal, aperture grid, and then here's the silicon photodetector, and then the metallization up on top, on the back. So according to the Taiwan Semiconductor Manufacturing Corporation, which is probably the world's largest foundry, makes silicon wafers for a lot of companies, this is what they think the trend will be. So this is pixel size from 4 microns down to 0.7 microns. And they think that basically in this pixel size range, it goes from about 1.4 and up, is the conventional front-side illumination technology. And now just coming on the marketplace in real products today is backside illumination, starting somewhere in this range. Typical values are 1.4 microns or 1.1 microns or even 0.9 microns. Well, these pixels are getting really small. Another way to try to improve the performance of each pixel is to make each pixel do more. So if we consider just a piece of silicon, here's a, let's say it's 1 micron by 1 micron and maybe 3 microns deep. So we have a little slab of silicon. The light comes in, generates electron hole pairs. Different wavelengths of light get absorbed at different characteristic lengths, over characteristic lengths. And that's because, for example, blue light has a lot more energy than red light. So if a blue photon comes in, it's easier for it to break one of those covalent bonds, more likely that it'll break one of those covalent bonds than a lower energy red photon that comes in. So a blue photon, when it comes in, pretty much it breaks a bond and the light is absorbed right near the top surface here. Whereas red comes in and it actually can go quite deep into the silicon before it's completely absorbed. And green is somewhere in between. So if we consider that RGBG Bayer pattern I showed you before, here are the 4 color filters and the pieces of silicon. Light comes in, the blue gets absorbed mostly up here, this green light gets absorbed, of course it gets absorbed everywhere, but say in this region, and the red of course is much deeper. If this is a small pixel, we get kind of these signals out of these things. Like for blue, the blue channel, I'm sorry, this is straight out of my computer program, by the way. This is the blue signal as it comes out raw. Ideally, we'd like it to look like this dash curve. And after we apply the color correction matrix to these signals, we get something that maybe is this fatter blue curve. Not quite perfect, not quite ideal, but better than what we started with. Same with the green and the red. We wind up with some negative coefficients and some other things going on, and not much light getting in. The net result is that the signal-to-noise ratio for luminance, I'm sorry, now I've jumped to like professional grade image sensor parameters here, but the YSNR, the luminance signal-to-noise ratio, is only about 6. And the customer requires about a signal-to-noise ratio of about 10 in order to accept this part. So we're in trouble. This is the conventional technology, and this is almost the best we can do at a 0.9 micron pixel pitch. So we got to do something different. One thing people have done, not directly related to small pixels, but related to being more clever, is to consider that absorption of light that comes in and think about, let's make 3 layers in the silicon stack, layer 1, layer 2, and layer 3. And the photons come in, and maybe in the first layer, it's mostly dominated by blue absorption, or blue photons, and the second layer by green, and the third layer by red. And if we plot the response versus wavelength for layer 1, you see that most of its response is in the blue, and for layer 2, it has a big response in the green, which is 550, kind of broad. And layer 3, sure enough, all the blue light's absorbed up here, it doesn't get down here, so there's no response in the blue for this layer, and then it kind of picks up. And we kind of get 3 different color signatures out of these 3 layers. Hey, that's great, because remember we had the red, green, and blue, we had to do the color interpolation, and we got color aliasing and that moire effect. If we do this, we don't get that anymore. That's great. But the problem is that because these signals overlap so much, the color quality and the noise really suffers. So kind of a good idea, but and people have made products. In fact, Sigma cameras tend to use these sensors, but unfortunately they're not that popular. It's a very, very small percentage of the market. They have a lot of problems. mostly just because it requires so much processing to get a good picture out. On the other hand, I have to say that they do produce some very, very high quality pictures once you do all that. Anyway, here's an idea that I was working on, which involves kind of an in-between approach. We have 2 layers as before, and we have 4 pixels though, and we let white light come in through these pixels and green light into that pixel, and this pixel with a magenta filter just allows blue and red through it, blocks green. And we can say that the blue is absorbed in this layer and the red is absorbed in layer 2. So we get at least 3 pixels that have a very strong luminance signal, and just basically one of those 4 pixels is used for the chrominance signal, the blue and the red signal, which we don't care so much about the noise in those signals. We care mostly about the noise in the luminance. And again, if we work through what we start out with and going through a color correction matrix and calculate what the signal to noise ratio is, we see that the signal to noise ratio increases to maybe 8.85 or 9, which is very close to what the customer needs. So from that point of view, hey, maybe doing these extra layers gives us better performance. But my own personal opinion after doing this is it didn't work half as good as I thought it would. Which is usually the case in research. So one of my graduate students reminded me, he says, there's a reason why there's an RE in research, because we do it again and again and again. That was on a bad day, he told me that. Anyway, the point is that in order to actually make this device, even though the performance is good, probably costs too much to justify the improved performance. And that's where kind of the business decision comes in. Okay, moving on to small pixels. Hey, we have a real problem also, that we can't make the pixels really tiny without thinking about the diffraction limit. If you start with a perfect point light source and you go through a lens and it's a perfect lens, you still wind up with a diffraction pattern. It's kind of an airy disk pattern, which is more or less fundamental. It's called the diffraction limit. And it depends on the wavelength, and it depends on the F number of the optics, according to this mathematical relationship. And if we pick some wavelength like green, 550 nanometers, with a f2.8 lens, that's what's typically used on a camera phone, we find that the diameter of this inner spot, which used to be a perfect point, is now something like 4 microns. So, that's kind of an issue if we are dealing with, let's say, 0.9 micron pixels. We want to form a small, tiny spot on here, but actually the airy disk is already this diameter. So it's kind of a marginal return on shrinking the pixels for resolution improvement. On the other hand, when I worked at Hughes Aircraft Company, back when there used to be a Hughes Aircraft Company, our favorite saying was, well, if you can't fix it, feature it. So, hey, look, it's kind of, we don't need that anti-aliasing filter anymore, because the signal's already spread out for a bunch of pixels, so we won't have any color aliasing problems. But anyway, there's some real practical limit to how small we can make the pixels. And, there's been what they call the megapixel race. People try to put more and more megapixels, and I think that it's actually starting to slow down. I think when we get to 1.4 micron and 1.1 micron pixels, we'll see less emphasis on the pixel count and more emphasis on other functionality in the camera. We're already starting to see that now. Higher dynamic range, extended depth of field, slow motion image capture I talked about before, handshake blur reduction, where there's some image processing so that when you're trying to hold the camera steady and you're shaking, it corrects all that, which it does by taking a very high frame rate image and then trying to correlate all these images and put them back together where they're supposed to be. I'm not going to talk about this too much. This is just one example of high dynamic range imaging and how you do that. The high dynamic range means that you have a very big range between dark parts of the image and bright parts of the image. Kind of like you're driving in a tunnel and the end of the tunnel, it's really bright out there, and you want the car's camera system to be able to see both inside the tunnel and outside at the same time. Does that mean the rapid?
Yeah.
What's that?
It is a hint, yes.
It's a hint, okay. Well, you know what, I don't care about this part of the talk. I want to talk about what I want to do in the future, which is jot sensors. How long is your hint?
Oh, I think people start squirming in about 3 or 4 minutes.
All right, so high-speed readout. Anyway, suppose you want to go really small. Consider a really tiny pixel or a jot that's sensitive to a single photoelectron, and the jot state changes from a 0 to a 1 when a photoelectron is present. So we're going to need some sort of single electron amplifier or single electron transistor that allows that to happen. And we're going to want billions of these on a single chip, so they must be small, like 0.1 microns on a side. And we were just talking about 1.4 micron pixels. This is 100 times smaller in area. And at a 0.1 micron jot pitch, a 16:9 aspect ratio sensor would be only a 1/4 inch in diagonal, which is very small. And one way this could work is that you take your normal RGB pixels and you divide them into little tiny jots. So they're very small, kind of tall, thin things. And the idea is that they can either hold 1 electron or no electrons. Now, in this case, there's only 64 of them here, which is a lot less than what you need for a normal image. So the only way you can handle a couple thousand is to read it out multiple times, maybe 80 times in a single frame. I'm going to skip that. And there's a lot of interesting things with this kind of architecture. It's a real digital image sensor. We're just taking single photoelectrons and that's it. And everything else we do to create the image, we're going to do off-chip through, or on-chip, but through some sort of digital signal processing or software. And so in a way, it's a cop-out from an image sensor. It says, hey, you know what? Instead of building a high-quality image sensor, I'll just give you the raw data and you can figure out what the image looks like. But you can imagine that when the jots get hit with electrons, and there's darker areas and brighter areas that get illuminated. And we could take multiple frames of these things, and then we need to do some sort of digital signal processing. You can think of it as maybe a nonlinear 3D convolution in X, Y, and time, where you try to recreate what the old grayscale used to be just from these digital bits. And a lot of interesting things with this, which I guess you'll have to take my word for, but one of the things you can see right away is, if we change the size of this convolution window, we can immediately trade kind of the resolution of the image, right, because it's going to be about that size, against sensitivity, right? So if we increase this thing up, we can capture a lot more jots in the processing, but with a lot less resolution. So it's a little bit like film. We have big grain film that's very fast, and very fine grain film that's very slow. But here we can do it a priori. We already know what the result is and then adjust the convolution window to get the optimum result. Okay, so I see everyone is probably squirming. If you didn't get the hint already, you should be squirming. Anyway, so key points that I hope you take away at least one of these, okay, is that the basic concept of an image sensor pixel and camera on a chip, you have some idea about what that is. Maybe you have some idea about how color image is formed. Maybe you learned today something about shot noise or reset noise and fixed pattern noise. Got some idea about the driving forces and technology limitations for small pixel development. And maybe even in a little tiny bit I gave you on jots that they might be a future technology for imaging. So thank you very much for not leaving.
I think we have time for a couple of questions.
I'm going to let you moderate that.
Okay.
So you talked a bit about trying to shrink pixel size and try to maximize the number of megapixels basically that you can take at a time. I'm just kind of wondering what the
do this.
Right.
Fair enough. So maybe I want to just continue to zoom in and zoom in and zoom in. So, that would be the case where you want to capture more data or more resolution than your eye can see than you want.
In the multi-layer sensor, is there a reason not to put color filter in between multiple layers? Is it just a processing trick?
Well, even though I showed little separations, it's actually a continuous piece of silicon.
It is.
So try to insert some polymer going in there. So that could be a different thing.
How does the luminance
Well, I don't know. I want to know. I was talking today, for example, with another people. It's like, that's something that's really vexing me right now. It's like, I go outside, I try to see shot noise. I can't see it. I can see it on the video screen, but if I try to see it with my eye, I can't see it. I want to know why. Excellent question. I don't know.
luminance is so important. Why don't you have pixels without any color filter? Get kind of
Yeah, so the question is why not have pixels without color filters? And there's a trade-off, because we do want color information. And restoring the color information means we want to sample the color as best we can. But it's also true now that people are experimenting with sensors that have a lot of white pixels in them, clear pixels, like you say, with no color filter array at all. So we just get the luminance. Now green is almost the same as the entire response. So green versus clear is almost the same thing. But definitely changing the ratio that's in that original Bayer pattern is a lot of interest. It does make the color process